So let's continue with our physics paper 1 SPB 2021. Alright, so we have question 31. Diagram 24 shows a battery with electromotive force E and internal resistance R. 0.5 ohm. Okay, our internal resistance is 0.5 ohm connected in series with a resistor 10 ohm. Okay, when the switch is on, a current I 0.3 ampere flow in the circuit. So first let's understand what is the meaning of electromotive force. So electromotive force is the work done to carry 1 coulomb of charge, to complete the whole circuit. Okay, the keyword whole circuit. Okay, and what is the internal resistance? So internal resistance is the resistance against the moving charge. So our electric current is carried by our charge. So internal resistance is the resistance against the charge in the source of the cell, which means it's our battery. Okay, so let's say for example, our electromotive force, which means our battery, supply a total voltage of 3 volts. Okay, so this is our electromotive force, and when the charge is starting to flow in the whole circuit, there will be an internal resistance, because there will be a resistance to against the moving charge because of the electrolyte. All right, so your internal resistance, for example, here will be 0. Okay, the internal resistance, okay, will cause the voltage to loss. All right, the voltage will need to against the resistance. So for example, we have 0.5 voltage loss due to the internal resistance. So the potential difference will be 2.5 voltage, 2.5 volts. So the voltage in the circuit will be 2.5 volts. So the internal resistance is due to the resistance against the moving charge, okay, in the cell, or the source of the cell. So this is against the moving charge. Okay, so this internal resistance is the resistance against the moving charge due to the electrolyte. Okay, due to the electrolyte. So understanding this, so we can get a formula. E, this is representing the electromotive force, equals to voltage, which is your potential difference, 2.5 volts for example in this case, plus the voltage loss due to internal resistance. So the current flow here will be the same because this is a series. So the series, the ampere in the whole, the current in the whole circuit will be the same. So we have IR, V equals to IR plus the same internal, currents, and multiply by the internal resistance R. So the R, the smaller R here representing the internal resistance. So because the I here is the same, so you factorize out, you will get IR plus small r. Alright? So which of the following statement is not true? I equals to 0.3 ampere. This is true because this is the series. So our whole circuit, okay, a series circuit, the whole circuit, that currents traveling in it will be the same. So V equals to 3 volts. So the volts here equals the voltage they want here is the voltage X here. Okay, so V equals to IR. So you will take the 0.3 multiplied by the resistance 10 ohm. You will get 3 volts. Okay, this is correct. So E equals to 3.15 voltage. So we just use this equation. So we just substitute in the value here. This is 3 volts. All right, and the voltage loss due to the internal resistance. So 0.3 multiplied by 0.5, you get 0.15 volts. So you sum up, you will get 0.15 volts. So the electromotive force is equal to 0.15 volts, and this is true. And V equals to E minus 10.5. So let's find out whether this is true or not. Okay, so from here we have this equation. So we just move the value. Okay, I just write it here because the space is larger. So V equals to electromotive force minus voltage loss due to internal resistance, and you will get E minus 0.15. Okay, remember this is what we find for the from the value given. So this is not true. So the answer should be donkey. Okay, 32. The diagram shows a graph of V against I to determine the EMF and internal resistance of a dry cell. So same, likewise, we just use the equation electromotive force equals to V plus VR. So you can observe here the y-axis is your voltage and your x-axis is your ampere. Okay, so you just move, become VR minus E, and you get IR minus your electromotive force. So from here you can observe that this is equal to your Y, this is your M, this is your X, and negative electromotive force is your intercept. Alright, so this should be okay. Sorry, there's a mistake here. So V equals to E minus VR. Okay, so E here will be equal to your intercept. Okay, your C, and this is your Y, and this will be your IR. So R will be your gradients. R will be your gradients, and I will be your X. So this is your C, and V will be your Y. Okay, so can you see that? So from here we know that the electromotive EMF is the intercept. So it's the intercept of V-axis. This two is correct, and our internal resistance is our gradient. Okay, it's our gradient. So the answer should be donkey. Diagram 26 shows a LED bulb labeled 240 volts, 25 watts. So what is the electrical energy consumed in when the bulb is lit up for an hour in the units of kWh? This is called kilowatts hour. Okay, so what is meant by here is that it means that when the LED bulb is supplied with 240 volts main supply, the LED will consume 25 watts of electrical energy. Alright, so what is the electrical energy consumed when the bulb is lit up for an hour in the units of kWh? Okay, so we have the equation P equals to ET, where P is your power, E equals to PT, and E is your electrical energy, P is your power, and T is your time. So because here the kilowatts, okay, and per kilowatts hour, so the T here is in hour. Alright, so the P here is in kilowatt. Alright, so 25 divided by 1000, because the question given, they want you to find in kilo, multiplied by your time which is in hour. Okay, so multiplies by 1. So your answer should be A. Okay, next, diagram 27 shows an electric rice cooker with a label 240 volts, 700 watt. Okay, so what is meant by here is when the electric rice cooker is supplied with 240 volts of main supply, then your rice cooker will consume 700 watts of energy, electrical energy, every second. Okay, every second. So what is the energy used by an electric rice cooker to cook rice in 40 minutes? So use back the equation, E equals to PT, but take note that the E here is given in joule. Okay, so your joule, the T here will be second. Okay, so you just plug in the value, 7 times 40 minutes times 60 seconds. Then you will find the value donkey. Okay, so the SI units of our electrical for our energy is joule. Okay, so the joule is in W, watts second. Okay, watt second. But in this question, this is no longer our SI units. It just simply wants another unit, which is not our SI units, is kilowatts per hour. So take note that here, this is the power, and this is the time. Okay, so basically they are the same thing, just that one is in second, one is in hour, and another is in watt. This is in kilowatt. They are the same thing. Okay. Okay. 35. A current-carrying conductor is placed in magnetic field. The direction of force in the current-carrying conductor is determined by using Fleming's left-hand rule, as in diagram 28. So you just remember F, B, I. Okay. So F is your force, B is your magnetic direction of magnetic field, and I is your current. So in this question, they want us to find the direction of force, so the answer should be A. Okay. 36. Diagram 29 shows a bar magnet is pushed into a solenoid. So this is the solenoid. Okay. This is the solenoid, which is connected to a zero-centered galvanometer. So just revision, galvanometer is used to measure small currents. They are more sensitive to currents as compared to our normal ammeter. Alright, so galvanometer is used to measure the small currents. So zero-centered galvanometer to determine the direction of induced currents. So we learned two types of law in the chapter 4, Form 5 chapter 4, electromagnetism. One is Lenz's law and another is Faraday's law. So what Faraday's law states is that the induced electromotive force, or the induced current, okay, is directly proportional to the rate of change of magnetic flux. Alright, so our induced electromotive force is directly proportional to the rate of change of magnetic flux. Okay, magnetic flux. Alright, and our Lenz's law states that the induced currents, or the induced electromotive force, always flows in such direction so as to oppose the change causing it, which means the induced currents will tend to flow in a direction that will oppose the movement of the something that caused the induced currents. Okay, so for example, our magnet is moving into the solenoid. So here is north. So in order to oppose the motion of the magnet, so here will be N, here will be S. Okay, because N and N, they repel each other. So they want the electric currents, the induced electric currents, will tend to oppose the motion that's called motion of the magnets that cause its that cause the currents to induce, right? So the N will oppose the motion, will repel the magnets. Okay, so we just use the right hand grip rule. Okay, so this is north, this is south. So because you want to oppose the motion, so the here will be north. Okay, so the other side will be south, and you will observe that the currents will flow in such a direction. Okay, the direction is following the direction of your finger. Okay, so this is how your currents flow. Okay, if the question is given in like this one is S, this one is N. Okay, so in order to oppose the movements of these magnets, the currents will flow such that here will be south, here will be north, and you just use the same right hand grip rule. So the currents will flow in such a direction. Okay, so your direction will be like this. Okay, so I hope you understand what I'm saying. So the answer will be Lenz's law, north south, north. Okay, here will be north because they want to oppose the motion of the magnets. Okay, so the answer should be A. All right. Next, 37. What is emitted by the nucleus 234 thorium when it decays to be a more stable nucleus? Okay, so we have three types of radioactivity decay. The first one is alpha, the second is beta, and the last one is gamma. So just remember that our alpha, it will emit helium atom. Okay, so the helium have 2 proton number and 2 number of neutrons, so the total will be 4 nucleon number. And our gamma, it will just release the energy, release the gamma ray without changing, without releasing any atom, which means that when the nucleus they decay, there will not be any decrease or increase in the proton and the neutron number. All right, and so because the proton number is 2, they release 2, so which means if the thorium is undergoing alpha decay, the 90 will be minus by 2 because they release 2 proton, and the nucleon number will be also minus by 4 because they release 4 nucleon number. Okay, so if this thorium is undergoing alpha decay, the equation will be like this: pH equals 2. Okay, they decompose, so 234 minus by 4, you get 230. 90 minus by 2, you will get 88 plus the helium atom. So when you sum up the nucleon number and the proton number, you will get back the same value as here. All right, so the gamma, they will not release anything. So if this thorium is undergoing gamma decay, it will be something like this. Okay, so there will be no change in the proton and neutron number, but it will release the gamma ray. So this nucleus, the distorted nucleus, is more stable than the previous the nucleus before releasing the gamma ray. And our beta decay, it will release an electron. So in beta decay, in the beginning, the neutron, okay, I just delete all this first. Okay, so in beta decay, our neutron will decompose into 1 proton and 1 electron. 1 proton and 1 electron. So 1 neutron Okay, 1 proton and 1 electron. Alright, so if your thorium is undergoing the beta decay, it will be the equation TH. They will become Pa 23491 plus an electron. Okay, so you can see here, okay, your neutron, you lose 1 neutron at here and you add 1 proton. You lose 1 neutron at the beginning, you lose 1 neutron at the thorium here, and then they will the neutron will separate into the proton and electron. So you can observe here, you add 1 more proton, but the total neutron number remains unchanged because you lose 1 neutron and you add in back 1 proton. Okay, so 37, the answer will be Doki. So 38, an energy of 2.5016 times 10 power 11 joule was generated from the fission of the uranium nucleus, 235 nucleus. So calculate the mass defects involved in the process of the nuclear fission in units of AMU. Okay, so we just use the equation, we just apply the equation, E equals to mc squared. Okay, so E is your energy release, C is your speed of light in vacuum or air, and M is your mass defect. And your mass defect here is in kg, is in unit kg. So you just plug in and you will get M equals to the 2.5016 times 10 power 11 and divide by c squared. Okay, you will get, okay, you will get 2.779 times 10 power negative 28. So this is your mass in kg. So 1 AMU equals to 1.66 power 10 times 10 power negative 27 kg. So you want to find the AMU, so you just take 1 divide, you just take this value divide by 1.66 times 10 power negative, you will get, okay, you will get 0.1674. Okay, so your answer should be C. Now, question 39. A bulb emits light with a wavelength of 5 nanometer. The 4.0 power of the emitted light is 5.5 watts. Calculate the number of photons released by the bulb. Okay, so we learned 4 equations. We have 4 equations. E equals to HF, E equals to or E equals to HC lambda. Okay, and we also learned that the power equals to NHF, where N representing your number of mole per second, or P equals to NHC lambda. So how this equation of power is derived from the E, because we know that power equals to ET. okay, energy per second, rate of change of energy. So we'll have HF over T and N. So and N, and then N is your number of mole, because your N representing the number of photons. Oh, sorry. So N is the number of photons. So N is representing the number of photons emitted per second. Alright, so the T, they can cancel out because T is per second and N is the number of photons emitted per second. So you will get NHF. Alright, so you just substitute in, okay, because this question they didn't give you the frequency, so we just use this equation. Okay, P you substitute in equals to N, H will be the Planck's constant, C will be the speed of light, and lambda will be 5 nanometer, which you need to convert into meter is 5 times 10 power negative 9. Alright, if this is micrometer, it will be times 10 power negative 6. So nano is 9, micro is negative 6. So the answer you get will be 5.5 times 5 times 5 nanometer divided by Planck's constant divides by the speed of light. And you will get 8. Okay, you will get 8. So finally, the last question. Diagram 13 shows a graph of activation energy VA against V to determine the Planck's constants. So we have E equals to HF, the equation. Okay, E equals to HF. So because this activation energy, okay, so let's understand what is the meaning of activation energy. So in a circuit, okay, with LED light, for example, when you supply, okay, let's say this is 0, this is 1, this is 2, this is 3. Okay, so when you supply the circuits with the LED and you supply 1 volt, the LED bulb will not light up. You supply 2 volts, the LED bulb will also not light up, because in order for the voltage, the LED bulb to light up, you need to first achieve the activation voltage. So when you supply the voltage 3 volts, then only your LED bulb will be lighted up. Okay, so activation voltage is the minimum voltage for a minimum voltage you need to supply to your circuit for your bulb, okay, or other electrical appliance to light up. So you need to first achieve the activation voltage. So from here we can know that activation voltage, this is in a electrical circuit. Okay, so we can convert this energy into another equation, EV equals to HF, because EV here representing the electrical potential energy, because when you involve this activation voltage, this is basically talking about involving the circuit. So this is you can convert the energy here into the electrical potential energy. So voltage here is your energy potential difference. E here will be your charge, okay, number of charge. So you just move in, your V will be your y-axis, your F will be your x-axis. So V equals to HE over F. Okay, so this is your Y, this is your M, this is your X, and plus C, which is they didn't show up here. You don't know what is the value, so we just leave it. Okay, so from here we know that the Planck's constants, okay, is the gradient. So M equals to HE. Okay, so this is the gradient. So you want to find out the Planck's constants, you will use the gradients multiplied by the number of charge of 1 electrons. Okay, so the answer should be B. Alright, so wish you luck for your next exam. Hopes my video helped you. So bye bye.